The gross demand load represents the total connected load of all electrical appliances and equipment within a building. To determine this, the formula employed is the connected load divided by the diversity coefficient. In the provided scenario, the connected load comprises lighting at 2000 kilowatts, convenience power at 1500 kilowatts, mechanical systems at 3000 kilowatts, elevators at 1000 kilowatts, and building systems at 1000 kilowatts. These values are summed, resulting in a total connected load of 8500 kilowatts. Given a diversity coefficient of 1.2, the gross demand load is calculated as 8500 kilowatts divided by 1.2, yielding approximately 7083 kilowatts. The net demand load, on the other hand, represents the gross demand load multiplied by the demand factor. The demand factor accounts for the typical load expected to be drawn by the various appliances and equipment. To calculate the net demand load, the gross demand load is multiplied by the sum of each individual connected load multiplied by its corresponding demand factor. In this case, it is 7083 kilowatts multiplied by the sum of lighting, which is 0.9 multiplied by 2000 kilowatts, convenience power, which is 0.1 multiplied by 1500 kilowatts, mechanical systems, which is 0.5 multiplied by 3000 kilowatts, elevators, which is 0.5 multiplied by 1000 kilowatts, and building systems, which is 0.8 multiplied by 1000 kilowatts. This is equal to 7083 kilowatts multiplied by 1800 kilowatts from the lighting, 150 kilowatts from the convenience power, 1500 kilowatts from the mechanical systems, 500 kilowatts from the elevators, and 800 kilowatts from the building systems. The sum is equal to 7083 kilowatts multiplied by 4750 kilowatts. But the answer is incorrect because it should instead be 7083 kilowatts multiplied by each individual demand factor. Therefore, the sum of each one needs to be added for a weighted average. Firstly, let's establish that the gross demand load equation is expressed as follows. The gross demand load is equivalent to the total connected load all divided by the diversity factor. The total connected load consists of the summation of individual loads, such as lighting, which is 2000 kilowatts, convenience power, which is 1500 kilowatts, mechanical systems, which is 3000 kilowatts, elevators, which is 1000 kilowatts, and building systems, which is also 1000 kilowatts. In this scenario, the problem states that the estimated diversity coefficient is 1.2. So the calculations can be set up as follows. Gross demand load is equivalent to the sum of 2000, 1500, 3000, 1000, and 1000 kilowatts all divided by 1.2. Adding them all up, we get 8500 kilowatts divided by 1.2. Therefore, the gross demand load is equal to 7083.33 kilowatts. Secondly, let's determine the net demand load. The equation is net demand load is equivalent to the gross demand load multiplied by the demand factor. However, there are individual demand factors for each of the types of loads, such as lighting, convenience power, mechanical systems, elevators, and building systems. Therefore, the equation can be rewritten as net demand load is equal to the gross demand load multiplied by the summation of each individual demand factor multiplied by each individual connected load. Net demand load is equal to 7083.33 kilowatts multiplied by the summation of lighting, which is 0.9 multiplied by 2000 kilowatts, convenience power, which is 0.1 multiplied by 1500 kilowatts, mechanical systems, which is 0.5 multiplied by 3000 kilowatts, elevators, which is 0.5 multiplied by 1000 kilowatts, and building systems, which is 0.8 multiplied by 1000 kilowatts. This is equal to 7083.33 kilowatts multiplied by the summation of 1800 kilowatts from the lighting, 150 kilowatts from the convenience power, 1500 kilowatts from the mechanical systems, 500 kilowatts from the elevators, and 800 kilowatts from the building systems. Therefore, the net demand load is equal to 7083.33 kilowatts multiplied by 4750 kilowatts. The problem in the answer given is that the gross demand load is not supposed to be multiplied by each individual demand factor. The net demand load represents the total power required taking into account the gross demand load and the effect of each demand factor. This problem is not very clear since it uses the term net demand load, but it does not clarify what it means. This can mean a variety of things, and some clarification may be helpful to establish the correct way to calculate. The net demand load could mean a weighted average. So one of the assumptions that must be made is what net means. If the word net refers to the overall impact of all the demand factors of each individual connected load, then the following equations can be followed, which are more standard in terms of understanding the net effect or impact. If the net effect simply means the gross demand load multiplied by the demand factor, then there needs to be an established demand factor for the entire building complex. If that number is not established, then the individual demand factors are not able to be used in that way. It must instead be used to derive a weighted average or effect on the gross demand load. Firstly, we establish the gross demand load, which we already did. We add up all the connected loads such as lighting, which is 2000 kilowatts, convenience power, which is 1500 kilowatts, mechanical systems, which is 3000 kilowatts, elevators, which is 1000 kilowatts, and building systems, which is 1000 kilowatts. These individual connected loads are divided by the estimated diversity coefficient of 1.2, giving us a gross demand load of 7083.33 kilowatts. Secondly, we need to determine what the demand factor is for each individual connected load, which we know, as they are listed in the problem. Lighting is 0.9, convenience power is 0.1, mechanical systems is 0.5, elevators is 0.5, and building systems is 0.8. Thirdly, we need to establish the maximum possible demand without taking into account the demand factors. This is established as the summation of each individual connected load. Lighting is 2000 kilowatts, convenience power is 1500 kilowatts, mechanical systems is 3000 kilowatts, elevators is 1000 kilowatts, and building systems is 1000 kilowatts. This is equal to 8500 kilowatts. Fourthly, we can determine what the average individual demand factor is. This is expressed as the demand factor for lighting multiplied by the connected load for lighting added to the demand factor for convenience power multiplied by the connected load for convenience power added to the demand factor for mechanical systems multiplied by the connected load for mechanical systems added to the demand factor for elevators multiplied by the connected load for elevators added to the demand factor for building systems multiplied by the connected load for building systems, all divided by the total connected load without demand factors. So the average demand factor is equal to 0.9 multiplied by 2000 kilowatts plus 0.1 multiplied by 1500 kilowatts plus 0.5 multiplied by 3000 kilowatts plus 0.5 multiplied by 1000 kilowatts plus 0.8 multiplied by 1000 kilowatts, all divided by 8500 kilowatts. This is equal to 1800 kilowatts plus 150 kilowatts plus 1500 kilowatts plus 500 kilowatts plus 800 kilowatts, all divided by 8500 kilowatts. This is equal to 4750 kilowatts divided by 8500 kilowatts. Therefore, the average demand factor is 0.5588. Fifthly, now that we have the average demand factor, we can determine the net demand load. The net demand load is equal to the gross demand load multiplied by the average demand factor. The net demand load is equal to 7083.33 kilowatts multiplied by 0.5588, which is equal to 3958.33 kilowatts. The gross demand load of the building complex is 7083.33 kilowatts, and the net demand load of the building complex is 3958.33 kilowatts. Another way of thinking about the demand factor is the ratio of the maximum amount of power used to the total amount of power available. Therefore, it can be said that the demand factor is never greater than 1. A demand factor of 1 means that all the power that is available is being consumed. A demand factor of less than 1 means that only a portion of the power available is being consumed. The lower the demand factor, the less of the power available is being consumed at any given time. This means that the power distribution system does not need to be designed for all the connected loads operating at the same time, which would be a demand factor of 1. Using the concept of the demand factor helps save money because the electrical system doesn't have to be overbuilt. The diversity factor, which is in the denominator of the gross demand load equation, is the ratio of the sum of the maximum demands of the various parts of a system to the maximum demand of the complete system. It accounts for the likelihood that not all individual loads will be operating at their maximum demand simultaneously. The diversity factor is typically greater than 1. It is used to reduce the total load that the electrical system must be designed to handle. Therefore, the electrical system is more efficient and cost-effective. This also helps save money by allowing the engineer to not have to overbuild the electrical system. In summary, there are steps to determine the gross and net demand loads of a power distribution system. Firstly, determine the gross demand load, which is the total connected load divided by the diversity factor. Secondly, determine the average demand factor. This is equal to the summation of the demand factor multiplied by the connected load for each portion of the electrical system, then divided by the total connected load. Thirdly, determine the net demand load, which is the gross demand load multiplied by the average demand factor. When calculating the gross demand load and net demand load, it's important to consider the specific characteristics of the building or facility being analyzed. Different types of buildings have different load profiles and usage patterns. For example, an office building will have different lighting and equipment loads than a hospital or a manufacturing plant. It is also important to consider any future changes to the building or facility that may impact the electrical load. For example, if the building is planning to add new equipment or expand its operations, the electrical system may need to be upgraded to handle the increased load. When designing a power distribution system, it's crucial to select equipment and components that are appropriately sized for the calculated demand loads. This includes transformers, switchgear, cables, and other electrical devices. Oversizing equipment can lead to unnecessary costs, while undersizing equipment can result in overheating, voltage drops, and potential equipment failure. The National Electrical Code, or NEC, provides guidelines and standards for sizing electrical equipment based on the calculated loads. Following the NEC ensures that the power distribution system is safe, reliable, and meets the minimum requirements for electrical installations. The demand factor is used to determine the appropriate size and capacity of the electrical system. By accurately estimating the demand factor, electrical engineers can optimize the design of the power distribution system, reducing costs and improving efficiency. It's also worth noting that demand factors can vary depending on the type of load. For example, lighting loads typically have higher demand factors than motor loads. This is because lighting is often used continuously, while motors may only operate intermittently. Therefore, it's essential to consider the specific characteristics of each type of load when determining the demand factor for the building or facility. In addition to the demand factor, the load factor is another important parameter to consider when designing a power distribution system. The load factor is the ratio of the average load to the peak load over a specific period. It provides insight into how consistently the electrical system is being utilized. A higher load factor indicates that the system is being used more efficiently, while a low load factor suggests that the system is underutilized. By analyzing the load factor, electrical engineers can identify opportunities to improve the efficiency of the power distribution system, such as implementing energy-saving measures or optimizing equipment operation. In summary, calculating gross and net demand loads is a crucial step in designing an efficient and reliable power distribution system for a building or facility. Understanding the concepts of diversity factor and demand factor and considering the specific characteristics of the electrical loads allows electrical engineers to optimize the design of the system, reducing costs and ensuring safe and reliable operation. Accurately estimating demand loads is important for several reasons. Firstly, it ensures that the electrical system is adequately sized to meet the building's power requirements. If the system is undersized, it may not be able to handle the peak demand, leading to power outages and equipment damage. Secondly, accurate load calculations help to minimize energy costs. By optimizing the design of the electrical system, engineers can reduce energy losses and improve overall efficiency. Thirdly, proper load calculations are essential for ensuring the safety of the electrical system. An overloaded system can overheat, potentially causing fires and other hazards. Therefore, it's crucial to perform accurate load calculations to ensure that the system is operating within its safe limits. In addition to the factors discussed earlier, it's also important to consider the impact of harmonics on the power distribution system. Harmonics are distortions of the electrical waveform that can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with sensitive electronic devices. To mitigate the effects of harmonics, engineers may need to install harmonic filters or other mitigation equipment. These devices help to reduce the level of harmonics in the system, improving power quality and preventing equipment damage. In conclusion, designing a power distribution system for a building or facility requires a comprehensive understanding of electrical loads, demand factors, and other relevant parameters. By performing accurate load calculations, selecting appropriate equipment, and considering the impact of factors such as harmonics, engineers can ensure that the system is safe, reliable, and efficient. This not only reduces energy costs and minimizes the risk of equipment failure, but also contributes to a more sustainable and environmentally friendly building operation.